Are we here? Are we here? Are we here? Hello. Let me check mine. Hello. 22nd, 27. Okay. Not too bad. This stream is going to be about viscosity. It's about um the video, if you wonder. It's supposed to be the video about me doing the experiment, as well as uh, explain. And you see in this stream. I mean, I can just do like that, but I have an idea. I have my notebook. I have OBS Studio. I don't know what it's called. This recording studio is here. I have my camera. I have PowerPoint. So why no what? Why don't we present it? Oh yeah, I also forgot to mention. We also have YouTube. We have YouTube, and it's free. So why don't we just stream it? Well, furthermore, let's begin. Don't want to waste time. Anyway, viscosity. Let's talk about viscosity. When we think of viscosity, it's about the sticky of the liquid. The more viscosity it is, the more sticky. For example, if you compare the water and the jam, a jam like honey jam, oh no, not honey jam, like strawberry jam, the water is going to have less density, and the strawberry jam is going to have higher density, which if you can say the strawberry jam is more sticky. But before that, let me get into this video first about me making the video about viscosity experiment. Why do I have to separate? Why not? Let's begin. Right, this is boring. So what do I have here is what do we have here is uh the container, this container, this cylinder container, and the rubber bouncy ball with the scale. I made a scale from it. This experiment is not going to be that accurate, unfortunately, because I have to measure the ball and the container, the radius, the height, as well as the scale for looking later on. And the sphere is pretty hard for a regular ruler to just measure it. Anyway, I think I muted anyway. It's alright so you don't get mixed with my voice and this person's voice. So here, this is the container. To have here is the total of around 10.5 centimeters, and this here is 5 centimeters supposed to be. This is here is 10 and around 0.5 around here. We start the bottom around here. That's like the thickness of the container. So I'm starting first with the air. Surprisingly, the air itself is considered as considered to have viscosity. Why? I don't know, but it can be really useful later on. So yeah, I draw. It should be like the bouncing doesn't count. It's going to be like I drop it here, I drop it, and as soon as the frame rate hit that's it for the experiment. The water, the bottom, that's it. That's for the water. It's gonna hit around here, and we have to look at the video in which I already did explain it later on. So here's the water. Here's the annoy. This annoy, not annoy, and oil. Starting from here at the top, 5 centimeters. Drop. Done. The last one, honey. I drop it. It's floating for a while. This can be difficult from others liquid because liquid doesn't only have viscosity property, it also have the buoyancy of the ball. If you look at this experiment, the buoyancy, the viscosity, and many other factors. So this experiment is going to be a rough one. But through it, that's the end. That's me. I think somehow I wore the same shirt. This is like 8 days ago. I'm wearing the same shirt. I am wearing the same shirt. Right, let's go back to experiment. So now when we already look at the video, let's see. So as I was mentioning before, it's about the stickiness, the sticky of the liquid. But I have a little bit of a model for you to look of how does it work or why is it sticky. So here's you imagine a drop. This is a drop of water or some liquid. So you imagine a drop has a layer between itself and with the surface, obviously. And this, the big thing here is the layer I'm made to represent. This is the surface, the layer between itself. And look what happened here when it's got pulled, whatever is by gravity, wind, or etc. It's going to move forward. It's going to move forward here even more. Oh, I didn't see even more and drop down because well, let me okay. So why is the upper layer is in front of the lower one? It's because the upper the layer, the faster it goes. So if you compare the speed, the topper one is going to be faster, and the lower one is going to be always going to be lower, which means the friction happens. So imagine you have a faster and a slower one. The slower one is kind of act like it pulls the faster one because they stick together of the because of the adhesion. The way that adhesion works is the object bond or sorry connect with other objects, but the is kind of similar to cohesion in which object connect to itself, same molecule, but the adhesion is different. So they kind of connected by adhesion, in which making the lower one cause of friction. They cause a friction. They all happen in every layer of it. which mean the different the layer speed, the sticky, the friction it has, which cause viscosity, different layer. Um, okay, so here is formula that you have to get used to it. We're going to talking about it for a while. Viscosity, use this symbol, or maybe you can see it like a long N. So you use that later on. Distance, D, meters. Oh, this is per second. This is area, density, mass, torque, weight, and this is some formula for to find the density, specific weight, uh, so on. But we are going to use this formula and the special one for our experiment. It's going to be specific for that experiment. But first, before we go there, we let's get used to it first with some of the equation I'm prepared here. Starting with equation 1. A stone has a mass of 2 kg and a volume of 0.001 meters square. What is its density in kilometers per meters sorry, not square, cube, meter cube? So how are we gonna solve this? The given is mass 2 kg. The volume is 0.001 meter cube. What we don't know is the viscosity. Oh, sorry, the density. So we're going to use this formula, density, um, like this, and weight. Just put the formula in it, and we get we will get 2000 kilometers per meter cube for the density. That's for the first one. And for the second one is a liquid experience a shear stress of 2 par, and the velocity gradient is 4 1 over second, like this. What is its viscosity? So they give us the stress, shear stress 2 par, and the gradient. The gradient is the du over dy, in which is this one. They also give the shear stress, or the torque, basically, which is that one. And they ask for the viscosity, but we only have this formula. What are we going to do? Torque, viscosity, du dy, move this to the other side. Torque, du, sorry, du dy, and viscosity, which we have 2 over 4. We'll get 0.5 per second. Is that right? But let me check. I don't really sure this one. Is that right? I feel there's something wrong. Oh yeah, sorry, right. Yeah, my dumb stupid. Just yeah. So here is the gradient I'm talking about. There's going to be a shape of a graph. In a graph form, it's going to be like this. With the friction I mentioned it before, layer, viscosity, this formula, and you can also check this video out down here. I don't really know if you see it, but it's about understanding viscosity. Very interesting. I also got this picture from that video. This is the formula. Right. So now, when we already get used to viscosity. Let's go back to this experiment and solve it with this formula, this very specific formula invented by Stokes in the name of Stokes formula. His name, this is his name. Right. You can also check the full video out. You can pause and copy, or I'm just going to send the link anyway with the video and the report. Right, Teacher Bell? Right. So from the video, the container is 10.5 centimeter high, or around 0.125 meters. The radius here 0.0225 meters, and this is for the empty one, the empty. But there's also for the fluid, so the height is only 5 centimeters, or 0.05 meters. And for the rubber's bouncy ball, radius is 60 centimeters, or around 0.016 meters. With the stroke formula, we have 2 over 9 densities minus densities times gravity times radius square over by velocity of time. So 2.9, we already got it. This density is for the rubber bouncy ball or the balls. This one is for the liquid, which we change. The gravity is constant. Radius is use the container radius. VT also different in different liquids. So starting from the ball, the density of the wall, how do we find it? How did I find it? I used the formula of density is equal to mass over volume. This is supposed to be it. Sorry. So for my experiment, I didn't measure the mass of the bouncy ball. So I searched online about this site, specific site, the solid rubber bouncy ball, and it gave me around 1.717 times 10 to the power of negative 5 kilogram, and over by the volumes, which is 3 or 4 3 pies times radius cube, and we get this density for the balls. And now moving on to the density of each liquid. So from the video I got 4 different types: the air one, the water, oil, and honey. So this all density I got it from Google. So from air, water, oil, and honey. I use each little letter for display each liquid. So for the air it's going to be A, W is for the water, oil, O, or 0 in this case. Honey is H, and the density of the ball is B, big B. Alright, moving on to the liquid. Each liquid has different velocity. From my video that I calculated, we can look at in here. This is what I calculate: velocity over mass per second, and my video is 30 frames per second, so it's going to be around, so my one frame is going to be around 33.133 milliseconds. So if you add up together, the 30 frames is going to be around 1,000 milliseconds, which is equal to 1 second. I explain here. This is from air, 10 centimeters for frame, etc. We got this. For the water, we got this. Oil, we got this. Honey, we got this. That's how I get the velocity from each liquid. Right. So this is I put it to density of bowl. This is the density of each liquid, which can be changed if we talking about air. This is going to be A, water, oil, and honey. So let's start off with the air. This is viscosity, if you remember. We can write like this or like this. Right, we got 2. What's the ball again? Not this one. Um, 1,100. Right, 1,100 minus. We're looking for air. 1.225. 1.225. Gravity is constant, which is 9.1 or 9.81. Radius of the container is this one, 0.0325 meters square. So we have 9. The velocity of the air is 0.75. We calculate together. We're going to get around 3.37 per second. That's for the air. So this is what we have here. The air for air, water, oil, and honey, as well as the velocity of each, which we already calculated the first one. Answer around 3.37 per second. What about this one? Look at here, 1,000 for the water, 0.667 for the water as well, but in velocity. Put in here, you're going to get around 0.345 per second. Oil as well. This is your voice 920, which is surprisingly lower than the water. But it's very weird than the water somehow. For me, it's for me myself. I feel like the an oil is more sticky on my hand than the water, but somehow it's less. Anyway, velocity is 6.0006 meters per second. Put it here and get around 0.027 per second. This one we get around, oh, this is for honey. This one we get around negative 36 per second. You see here, this is negative. Why is it negative? If you look back in the video, we're going to see that the honey is floating. So it shows that the ball is floating for the honey. This is because by the buoyancy making it float. That's why negative. And now you may start to curious. What am I going to do with this? Why do I have to learn the viscosity? Why do I have to know the unliving object that I drink every day? If I eat honey every day, I eat it every day. I using cooking oil every day. Why do I have to learn about it? Well, You say we use a lot of things, yet sometimes we have to understand it in order to make it work. For example, the vehicle. If you speak of viscosity, first one of the first thing you're talking about oil, and if you're talking about oil, it's about engine, it's about car, and each car have a different engine. So for the gasoline engine, we're going to use a gasoline. For the diesel engine, we're going to use diesel, and they both not really have quite the same viscosity, which can affect the motor, as well as we can use it for the design of the vehicle. As I was mentioned before, the air is considered to have a viscosity, and as well as aerodynamic, but viscosity also count. So the stickiness is still affect on our car, our jeeps, our plane. So we can use it to calculate the good shape for the vehicle. But why do you have to care about vehicle? I don't care. I don't like car. Well, you eat food. You eat food. So sometime in the morning, you just don't have enough time to spend on food. You have to be hurry. You're rushing to get to school, work. Viscosity can help you making it faster. For example, honey, it's sticky. It's sticky. It's slow. You want to rub it on your bread. It's slow. How can you fix it? Heat it up. You can heat it up. Making it faster when you pour it on your bread. Or even a cooking oil on a pan. You see when if you cooking, if you ever cooking or frying something like pork or chicken, you see the first when you pour the oil, it's not that sticky as a honey, but not really that fast. But after you put it in the pan and you heat it up, it's move faster. If you heat it up, not you heat it up enough, it's faster. The movement is faster. You bend it, you um make an angle. It's faster. It's more faster. It's make your oil separate around the pan faster. Imagine you have a big pan. If you just want to scatter it now, not heat it up first, it's going to be slow. But if you heat it up first, it's going to be fast. The same for the honey. Oh, sorry, for the butter. Imagine you have in the fridge. It freeze. It is solid. If you put it in the pan, you put the heat. It's melt. Yeah, that's also about the melting, but it's quite well viscosity also in there. Just tiny bit, but still in there. Cooking, and maybe you can also look at DIY entertainment. Maybe you want to stick something together, do some a little crafting. Use glue, sticky, sticky little substance, glue. You can use that, and that's the viscosity and other energy, but viscosity also in there, as well as slime. The sticky, slowly little thing that caused me trouble in elementary school. It's helpful, as well as a paint gun. The thing that you want to have it liquid, and when you paint it, you want to have it dry. You can use viscosity to solve it, not mainly, but part of it. So, aside from all that, I think that's all for my video, my stream. This is going to be the end. It's time to end this little teeny tiny video of my physics works. I would like to say thank you for everyone to be here. I don't know how much you're watching. I'm setting in public, even now when I'm live. This is public. I don't know who's going to click on it. I click on it about viscosity. You can also check the video I made. It's a 3 minute and 1 second long. It's quite long. I'll just cut it out. And this is going to be long. Anyway, it's the end of the video. Why are you still here? Go home. I mean, if you're already home, don't go home again. Close it. Close the video now. It's already the end. It's already end. Man, I'm not playing with the camera. It's already end. Why are you still here? Alright, you wanna hear me talking? I'm going to talk about the viscosity. No, psych. This is the end now. Bye bye. Bye bye.